Hello, I'm Norman Wildberger. In today's lecture, we want to continue what we were talking about in the last lecture, talking about colored spreads, blue, red, and green spreads, and how to interpret them geometrically, especially using our understanding of determinants as representing areas. Okay, a good place to start is with the familiar blue geometry. Here's our unit circle. Here's our formula for the spread between two vectors, vector u and vector v. It's in general 1 minus the dot product of u and v all squared divided by u dot u, v dot v. And this has an alternative reformulation in the case when u equals, say, ab and v equals cd, in terms of this kind of expression involving ad minus bc. This cross product between the two vectors, which represents the area of the parallelogram formed by them. And that's all squared, and under here we have the product of the quadrances of the two vectors. Okay, so we can have a look at this formula in a rather special case. And the special case is when we consider the unit circle in the plane, circle with the equation x squared plus y squared equals 1. And let's suppose that our vectors u and v are both lying on the circle. That is, they have quadrants 1. So if we position them to emanate from the origin, then their heads are actually on the unit circle. Then this situation becomes simpler because then these terms down here, the quadrances of the vectors, are just 1 each. So we get the following immediate consequence that if q of u equals q of v equals 1, then the spread s between u and v can be rewritten simply as u cross v squared. So in that case, we are just talking about the area of the parallelogram formed by them, all squared. That's a very simple, geometrical, easily visualizable interpretation of the spread between two vectors. Okay, so we have two directions. If we can find the points on those lines or directions that are on the unit circle, then it's just a question of looking at that area, that parallelogram, and taking it square. I want to contrast that with the much more familiar notion of measuring the separation of two lines. If you ordinarily have two lines like this and you ask a student, how do we measure the separation? They'll say, well, it's an angle. And what is the angle? Well, in this context here, the angle is exactly the area of this circular arc formed by the vectors u and v. But crucially, the angle one depends on a curved region. Okay? It's much more problematic, actually, to calculate the area of such a circular arc than it is to calculate the area of a parallelogram. It's like a difference of night and day. Huge difference. So let's shift to the red geometry, and let's see how much of that carries over to the red geometry. So here the crucial quadrants formula is that the quadrants of the vector AB is a squared minus b squared, as opposed to a squared plus b squared in the blue situation. And now things are a little bit more complicated because there's not just one unit circle. There's actually two unit circles that we need to consider. And one of them is the circle that describes quadrants equal to +1, and the other one is quadrants equal to -1. So x squared minus y squared equals 1, that's the equation of a hyperbola that looks like this. It passes through the point 1, 0 and -1, 0 on the x-axis. And then the hyperbola x squared minus y squared equals -1, that is this curve here. Also has two branches, but they're opening up and down, going through the points 0, 1 and 0, -1 on the y-axis. Now, these are hyperbolas, so they're not circles, but they are acting as circles in our geometry. So they play the same kind of role as the unit circle, the familiar round circle in the blue geometry. Okay, something that's a bit special about them, though, is that these hyperbolas have different geometrical structure. Specifically, they have these asymptotes. These two lines here, the lines x equals y and x equals minus y are things that the hyperbolas approach. So as we go further and further up there, then the branches of the hyperbolas get closer and closer to this line. And similarly in the other directions as well. So that's a rather special situation. Now let's observe that the meaning of the quadrants in this situation, I remind you that from our last lecture we interpreted quadrants in terms of being an area. Okay? So let's say we have a point like this one here, for example, or if you like, the vector emanating from the origin to this point. Then the quadrants of that vector in this red geometry is the signed area of this parallelogram. So if this is a vector, then this is what we sort of called V super R. So it's kind of a reflection of the vector V in this line y equals x. And then these two points together with the origin will form this parallelogram here. And it's the area of that parallelogram that's really being captured by a squared minus b squared. More precisely, the signed area of that parallelogram. Now this parallelogram is quite interesting because if this point lies on the unit circle, one of the unit circles, then its reflection in this asymptote will lie on the other unit circle. So these 2 points are sort of symmetrically positioned, and it turns out, and we'll see this later, but it's interesting to observe at this stage, that this parallelogram here has the property that it's actually a square in the red geometry. That's actually perpendicular, that's perpendicular, that's perpendicular, that's perpendicular. And more interestingly, that the relationship between this side and this side is that this one here is actually tangent to the hyperbola at this point. Okay, so the perpendicularity manifests itself in terms of the tangent to the hyperbola at a point is perpendicular to the radius of that point. In other words, the line from the center of the hyperbola to the given point. So it's a very interesting little parallelogram there. That's capturing the quadrants of this vector, and it's a very pleasant situation. Okay, so it's certainly more complicated than the unit circle in the blue situation, but it's still very analogous, and algebraically it acts very much in a similar kind of way. In particular, it allows us, this diagram, to visualize the spread in the red geometry. So let's have a look at the red spread. We'll have u being the vector AB and v being the vector CD as before. Then the formula for the red spread between those two vectors is, here's the general formula that we use no matter what geometry we're in, 1 minus u dot v all squared divided by the quadrants of u times the quadrants of v. And here the quadrants are the red quadrants, and this dot product is also the red dot product. And we saw that this could be rewritten using a pleasant formula that's analogous to the Fibonacci formula as minus AD minus BC squared divided by the product of the quadrants. Or if we want to write it directly in terms of the vectors u and v, minus the cross product squared divided by the product of the quadrants. Okay, so this interpretation, this second interpretation involving the u cross v in the numerator, allows us a very pleasant geometrical interpretation of the red spread, just as we saw in the blue situation. So how does that go? So suppose that we have our vectors u and v, and suppose that they are on the unit circles. So that u is somewhere on the unit circle, either on the positive one or say the negative one, and v also is on one of those circles. Now they could both be on the same circle or they could be on different circles like this. We don't really care, as long as they're both on the circles. In that case, the quadrants of both of them will be either plus or minus 1, because this is quadrants 1 and this is quadrants negative 1. So the quadrants of u is plus or minus 1, the quadrants of v is plus or minus 1. And that means that this formula here becomes actually quite simple, because this denominator is either going to be plus or minus 1. and combined with this minus sign, it's still going to be plus or minus 1. So we get that the spread then is necessarily basically just u cross v squared with a possible sign, denoted by epsilon. This epsilon is going to be negative QRU times QRV, because these are things that are plus or minus 1, so they're equal to their reciprocals. And this quantity is necessarily plus or minus 1, depending on which hyperbolas the u and the v are on. Okay, and it's easy to tell which. In this case here, for example, the quadrants of u will be plus 1. The quadrants of v will be negative 1. And in this case, the epsilon here will be plus 1. All right, so that in this particular situation, the formula is telling us that the spread between the lines determined by u and v, that spread S, in the red setting, is equal to just plus the cross product of u and v squared. In other words, we take the familiar parallelogram formed by u and v, there it is there, and we look at its area, and we square its area. And that squared area, it's just the usual familiar area, is the spread between these two lines in this red geometry. This is very nice. So it means that given any two vectors, or any two lines, say, through the origin, and we're interested in what's the spread between them, it's pretty easy to see if we draw our hyperbolas and see where these lines approximately meet the hyperbolas, draw a parallelogram, measure the area of that parallelogram, square it, and then just multiply possibly by minus 1, depending on whether the two vectors are in the same on the same hyperbola, in which case you have to multiply by minus 1, or if they're on different hyperbolas, like here, you just take the square of the area. So a very nice, relatively simple geometrical interpretation of the red spread between two vectors. Okay, so let's go to the green geometry, which is a lot like the red geometry, but a little bit of a twist. Now the quadrants of a vector AB is the number 2AB. Okay, and then there are two unit circles, 2xy equals 1 and 2xy equals minus 1. And they're both hyperbolas, as in the red situation, but they're kind of rotated a little bit from the red situation and also expanded a little bit. So here is the 2xy equals 1 hyperbola. If you like, you could think of that as the graph of y equals 1 over 2x. And here is the 2xy equals minus 1 hyperbola. So I've been given this the name plus and this one the name minus. And these are both hyperbolas with asymptotes, the horizontal and vertical axes. Now the same interpretation of quadrants applies here as in the red situation. If we're interested in what does it mean, for to have quadrants 1, if something's here, it means that it has quadrants 1. What that means geometrically is that if you take the parallelogram formed by this point and its reflection in the x-axis, which will lie on the other hyperbola, then that is a parallelogram which is like a green square in this geometry. So all of these things are perpendicular here. And just as in the red geometry, it turns out that this line here is actually a tangent to the hyperbola through this point. So the claim then is that the quadrants of this vector being 1 is really the same statement as the fact that this area here is equal to 1, or possibly minus 1, depending on where exactly you are. So as you move up here, these parallelograms become sort of skinnier and taller, but they all have area exactly 1, or signed area plus or minus 1. And we can use these two unit circles in this green setting as a nice device to give us a physical understanding of green spread. So the formula for the spread between two vectors in this green setting is really exactly the same kind of story. We've seen it's almost the same exact formula, except that there's green quadrants is there. And so we get the same proposition as we did in the previous case, that if we have two vectors u and v, and their quadrants are both either +1 or -1, then the spread is going to end up being the cross product squared times some sign factor, epsilon, which is either going to be plus or minus 1, and it's this quantity here, minus the green quadrants of u times the green quadrants of v. So for example, in this situation here, there's the vector u, there's the vector v. So we might be interested in the spread between these two lines, the green spread between these two lines. So what we do is we see where this line approximately meets the unit circle, and where this line approximately meets the unit circle, or a unit circle. We take these 2 points and we form the parallelogram formed by them. Okay, this is no longer a square, this is just a parallelogram. And we take its area, and that area squared will be essentially the spread, but perhaps times -1. So in this case here, we have one of them being on the plus hyperbola and the other one being on the negative hyperbola. So in this case here, this quantity will be +1. And in fact, then the spread will be exactly the square of the area. But if this vector v was, say, like in this direction, was also on the same branch as u, so that we had, say, 2 lines like this, then we would expect the spread to be negative of the square of the parallelogram area formed by those 2 intersections on the with a hyperbola. So this is kind of a practical device that allows you to ballpark, good guess, as to the value of a spread given 2 directions in the green geometry. Now, when we were talking about chromogeometry, we saw that each of the 3 geometries, the blue, red, and green, were sort of controlled by a symmetric matrix. And in fact, we can be a little bit more general. We can consider an arbitrary symmetric matrix, and that gives us a more general notion of dot product. And it's very interesting, and turns out to be very powerful, to consider this more general situation. Okay, so we've already talked a little bit about this form of the general dot product. So here's a generalization, where now we have a general symmetric matrix in here, LMMN. That's a symmetric 2x2 matrix. And this product then is determining a new general dot product. So we won't put any color here, but this is some kind of new dot product. So AB dot CD is this quantity here. When you multiply it out using just basic matrix multiplication, you get the quantity L times AC plus M times BC plus M times AD plus N times BD. So we're taking products of entries, 4 possible products between the elements here and the elements here, 1, 2, 3, 4, and each of those 4 products gets multiplied by a factor, with the BC product and the AD product getting the same number. That's the symmetric condition. Okay, so in mathematics, this is called a symmetric bilinear form, and it's a kind of a staple of sort of abstract linear algebra. And associated to it, there's a quadrants. So once we know how to take the dot product between 2 vectors, we can take the dot product between a vector and itself, and we'll call that naturally the quadrants of the vector. So the quadrants of the vector AB in this context is AB dot AB, and then that becomes L times A squared plus 2MAB plus NB squared. So these 2 things here become equal, give us this 2MAB. And this is the associated quadratic form associated to this bilinear form. This bilinear form has sort of 2 entries, a vector and another vector. This quadratic form only has 1 entry, or 1 input, the vector, and it's quadratic in the elements of the initial vector. Here the elements, the entries here are sort of bilinear. They're linear in A and B and linear in C and D at the same time. So this is a very general situation. We have a 2 by 2 symmetric matrix. We can define a dot product. We can define a quadrants. We can do geometry. This is a direct generalization of our understanding of blue, red, and green geometries. And it turns out to be very powerful thinking. Very powerful. Okay, so now carrying on with this new geometry, natural thing to do is to introduce perpendicularity of vectors. Of course, this is a new kind of perpendicularity that's suited to the geometry that we've got. And the definition is the same definition as before, that u is perpendicular to v precisely when u dot v equals 0. And then we get Pythagoras' theorem, which is that this perpendicularity that we've just defined is basically equivalent to this equation or relation between three quadrances. Between the quadrants of a vector u, the quadrants of the vector v, and the quadrants of the difference v minus u. So if quadrants of u and quadrants of v add up to the quadrants of v minus u, then these two are perpendicular. Okay, quadrants here plus quadrants here equals quadrants here. That means that we have perpendicularity there. And the proof is really exactly the same as we've outlined in Wild-Trigg 74. If you look at that proof, you'll see that it applies in generality. So it's the same story. Okay, so having quadrants and perpendicularity, the next obvious thing to do is to define the spread between two vectors. And we use the same formula as always. The spread between vectors A, B, and C, D in this new context is the same as it always is. It's 1 minus the dot product between those vectors squared divided by the product of the quadrances of the vectors. And now since our dot product is given by this matrix, let's give it a name, M, which is LMMN. Then, well, the dot product becomes this expression that we've just written down, LAC plus MBC plus MAD plus NBD, and that's all squared. And these quadrances down in the denominators here are just the quadrances. This is LA squared plus 2MAB plus NB squared, and this one is LC squared plus 2MCD plus ND squared. Now in the blue, red, and green situations, we saw that in each of those cases there was a somewhat miraculous identity that in the blue geometry goes back to Fibonacci and perhaps to Diophantus, that allowed us to rewrite this without a 1 minus, to rewrite it in a way that involved the cross product of the two vectors in the numerator, that basically that area squared. And it turns out, remarkably and beautifully, that the same kind of thing happens here in this much more general situation. With an arbitrary 2 by 2 symmetric matrix there, and so this rather more complicated thing, it turns out that this expression here can be rewritten identically in this form here. We see exactly the same kind of thing as we've seen before. There's the cross product squared, and here on the bottom are the two quadrances that we had there. The only difference this time is this additional factor which appears. Ln minus m squared. That, of course, is the determinant of this matrix. So we can rewrite this more succinctly as the spread between u and v is determinant of m times the cross product squared divided by the product of the quadrances of the vectors. So it's a significant exercise to establish this identity here. Basically, we're saying that if you take this thing times this thing and you subtract this thing squared, that it simplifies dramatically and you just end up with ln minus m squared times this cross product squared. It's fabulous. Okay, and it now explains what's been going on to a certain extent in those previous formulas involving the blue, red, and green situations. In the blue situation, the matrix here is the identity matrix 1, 0, 0, 1. It has determinant 1, and so this is just 1 and doesn't figure. In the red situation, we have 1, 0, 0, minus 1, and the determinant is minus 1. That's why there's a minus sign that appears in that red formula when we write it in this fashion. And in the green situation, we have 0, 1, 1, 0. Its determinant is also -1, and that's why there's also a minus sign in the green situation. Okay, but now we see the bigger picture, right? We see that this kind of story will work no matter what symmetric matrix we put up there, as long as this determinant of m is not 0. If the determinant of m is 0, then somehow all bets are off. This whole thing collapses, and our geometry becomes sort of degenerate. Not necessarily without interest, but it's no longer the same kind of rich geometry that we have in the blue, red, and green situations. So typically we'll be looking at the situation where the determinant of m is non-zero. So a whole new kind of world of geometry opens up here, the possibility of doing geometry in a much more general fashion, using a general bilinear form. We'll have a look at that more in our next video, and we'll make contact with a sort of an interesting program for triangle geometry that this allows us to see. So really exciting stuff. Lots of new developments here. We're sort of on the cutting edge here of a lot of new 21st century developments with this much more general approach to metrical geometry. Arising, of course, because we've understood rational trigonometry. It's all built up from rational trigonometry. If you stick with angles and lengths, you have no hope of really appreciating any of this, really, unless it's sort of added from a distance. Okay, so I hope you'll join me for all that exciting stuff next time. I'm Norman Wahlberger. Thanks for listening.